Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Ashish Darbari from Axiomise. We're going to talk today about verification of networks on chip. Ashish, why is it so hard to verify a knock? I mean, these things are getting very, very complicated. You've got chiplets, you've got multiple domains, you've got power domains, you've got all sorts of things going on. You've got data moving in lots of different directions. This makes a knock much more difficult to understand what's going on, but verifying this and making sure it's going to work is even harder, right?
Yeah, so Ed, the problem of knocks has been around for quite some time. Normally, knock verification was challenging, but not as challenging when coherency came into the picture. And as you know, knocks are needed as fabrics because we're trying to connect hundreds, potentially thousands of processing elements. And when you bring the Amber Chi protocol for handling coherency, or you think about splitting down knocks into smaller chiplets and bring the UCIe angle into it, you've got so many different protocol layers, network layer, link layer, down to the chiplet layer, so much concurrent traffic happening and so many different interactions now happening that it's almost impossible for any human being to conceive a complete set of test cases or verification scenarios. And we are seeing more interest emerging in the silicon design houses, entire bunch of architects, designers, and verification folks trying to tackle this beast. I think you guys are picking up a lot of this as well. I see from some of the posts that are going up on semi engineering. So I think we are resonating in terms of what we see in the industry, isn't it?
Well, let's take a closer look.
Sure.
Ashish, what are we looking at?
Right. So what we're looking at is the bug families that escape to silicon, not a comprehensive list, some of the bug cases that we have been seeing in the field through our interaction with the NOC designs and customers and open source NOC platforms. So what we've been doing is classifying them into different categories. So flow control accounting errors, very common source, ordering and serialization violations that actually become more perceptible and much bigger in impact when you talk about them in the context of coherence, state machine bugs that come from the chi layer. But even without the chi layer, ordering and serialization bugs can cause you the head of line deadlock. Arbitration, of course, causes live lock, starvation issues. Security, actually, inside channel paths is becoming a very interesting problem for NOCs, along with the old reset and clock domain crossing issues. Even now, with multiple power islands, you have these power domain crossing type issues. Just the integrity of bursts alone can be quite a significant challenge, especially in the light of AXI and Chi interleaving with each other across bridges. So making sure the response channels are responding to the requests, X-propagation issues that creep up because people use low power challenges. Control field mutation in transit is another interesting one. So loads of interesting types of bugs. We've been doing all kinds of interesting classification internally in Axiomise to look at the broader root surface of these bugs and how one relates to the other, what is the primary implicant, etc. So they're very, very hard to actually catch. And if they do leak to silicon, some of these can cause you a respin quite easily. So that's why the whole problem is actually quite hard.
What kind of bugs do you typically see escaping?
Right. So let me talk about something that has come up a few times in my conversation with customers. And then we happen to see this on a real design. So this is a silent data corruption. Now, this trace is a very interesting trace. What you're seeing on your screen is a waveform that shows an AXI ID ordering issue in a reorder buffer. And most NOCs that we work with almost always have a reorder buffer. So what happens is that the reorder buffer write responses go to memory locations that are indexed by transaction IDs. But when you get two consecutive responses with the same ID, written to the same address, what happens is that the earlier response is silently overwritten. And this bug is quite subtle in that the earlier response is written and you never really actually find out. One of the things we've been doing is to see how we can cache these more systematically through automation with knockproof, which is the app that comes with these kind of checks. So this kind of check would not be that easy to find very easily with non-formal techniques.
It's interesting that you're seeing silent data corruption inside a knock because typically, when most people talk about silent data corruption, they tend to look at it from a higher level of maybe it's the processor or the SoC that's causing it, and they don't really see it on the data movement side.
Yeah, so silent data corruption, this particular trace is a signature failure of a whole class of silent data corruption bugs that can happen in processor, can happen in cache lines, in SOCs, like you said, in fabrics, in the case of Knox. The basic principle is the same that something has been corrupted quietly without impacting anything on the outside. So long as the impact of the bug is invisible on the IO, the bug is very, very difficult to catch. And the only way to catch these kind of bugs in general is to build a very robust end-to-end formal methodology around considering all combinations of all transactors, interleavings, and monitoring the internal state. Although this bug was caught by an end-to-end tracker that we have written, but that's what we typically do for most designs. So we weren't particularly hitting on SDC only. We were looking to do a more end-to-end scoreboard, but we happen to have picked this up as an example.
Does this show up at all when you're doing simulation?
That's an interesting question. So let us look at this very same bug in the context of simulation. So in principle, yes, you can. It will be quite difficult to catch it quite easily. Your scoreboard would need to model the ROBs per beat at rest generation independently of the DUT. The environment would have to monitor internal ROB outputs, and the stimulus deliberately has to exercise the specific burst length and ID combinations that expose the bug. So in practice, most UVM environments, I don't believe have all of these things happening in the same test bench. The thing that I think will make it harder for simulation to catch is that it looks like a legal AXI transaction at the boundary. Scoreboard will often trust the DUT's address generation and the failure surfaces downstream, but the data corruption would be attributed to a software bug. So in principle, yes, but it would be very difficult in practice to find these. Even if you found one like you know now this pattern, to be able to orchestrate the right combination of stimulus with scoreboard with burst, it's going to be a little tricky.
Formal sort of takes us to a higher level in a different way. You've got a lot of proofs. Do these proofs converge to show some of this stuff?
So the answer is yes. Let me actually take a step back and explain to you what we are doing with respect to the proofs problem. So on this screen that you're looking at, you have got this property generation that is happening now a lot more with AI agents. Human beings write that too. We have bus protocol checkers, XProp, CDC, and whatnot. We have tons of properties and formalizer, footprint, and flow tricks. The problem we have is that everyone can write assertions, but proof engineering, which is the layer in the middle, is actually significantly hard to build robustly, consistently every single time to guarantee that you can get sign off quality formal results. So, what's happening here is that unless you can get the sign off quality formal to prove exhaustively, you cannot guarantee that there would be no respin. And for the kind of designs we are touching in our interactions with customers, the respins would be extremely expensive. So that's why we are investing a lot of time to actually minimize this gap between what is written in properties versus what is used for sign off. The biggest cause of respin is logic design bugs that comes from the latest Wilson research report from 2024. And the good thing is that formal is naturally well placed to handle these kind of bugs because we use logic in formal to capture the reasoning behind the intent. And that's what gets close to the bugs. So yes, formal is well suited to write properties, but you also then need to make proof engineering work at an industrial scale. And that is what we have been passionately pursuing, both in our service contracts, but also now moving into software layers where we are automating this so that we can make it more predictable and make it more fast and repeatable, which is the challenge that is very interesting to solve.
It's not so easy to write assertions, though, right? I mean, isn't that sort of the same as with AI? Are you asking the right question? Have you got your assertion exactly right?
So assertions in general are easy to write. The question is whether we are writing the correct assertion in terms of completeness, in terms of being able to check all the corner cases, and would this assertion written in this way be able to catch not just the bugs, but be able to prove exhaustively to get us a deterministic outcome. Not having a deterministic outcome means all bets are still off. All of this investment people have made in buying formal tools, hiring engineers to write properties, or using AI agents, it yields very little value. So it just becomes a random exercise, I would argue. So that's what we should be looking out for by starting well and then finishing so that we don't end up with these logic and design bugs creeping into our designs after they're taped out.
And when you think about the complexity of a knock, asking the right question is absolutely critical and very difficult. Same thing with writing an assertion because you're dealing with so many different elements, right?
Absolutely. So handling the concurrency of the NOC network layer is one, going into the coherent layer and actually capturing the artifacts of the protocol that handles cache coherency. Or if you go down a level from the NOC down to the chiplets to the UCIe, how does the whole traffic goes from the top to the bottom? So it's how the vertical traffic flows, how it is on the horizontal plane, where all the interactions at the protocol level are preserved. And all of these bug escapes that I talked about, X propagation or CDC or the deadlocks, they could emerge at any layer. So the verification plans and the structure of the verification test benches have to be thought out quite carefully, I would say. And that's what is the biggest challenge facing most verification engineers, including us. Even when you do formal, that is still the biggest challenge.
So we've been seeing a lot of respins, particularly on some of the most advanced chips that are going into data centers and some of the leading edge nodes. How much of that is being caused by the knock?
Right. So let's look at the primary cause of respin. And I think if you go to the industry data, they're not particularly characterizing whether it's a knock or a processor, but what they are characterizing here is what is the primary cause of most of the leaks to the silicon. And logic or functional flaws remain the leading cause of bugs. Harry Foster's Wilson research report has been very clear that design errors and logic bugs contribute to the biggest bucket of this. I don't think that the survey is getting to a level of granularity where it is able to decompose what percentage of these is attributed to NOCs or processors or GPUs or anything else. From the place where we stand in, we see a lot of NOCs and we do see a lot of bugs. I can tell you that in the last 3 to 4 years of having worked on different kinds of NOCs, we've easily flushed out 300 to 400 different kinds of bugs on different NOCs. So they tend to be quite easy to have a bug in. Compare it to some of the other work that we do, I would say those numbers are not as high as the NOCs in general.
And just to be clear, this isn't really about the knock, right? It's more about the ability to be able to pull all these different elements in from your design because there's a lot of different things that are where data is moving, being stored, coherency, all these
Yeah.
different challenges.
Absolutely. So it's a scale scale, problem of interleaving, problem of protocol layers interacting with each other. It's all of it. And it's just quite big because nobody's going to build a NOC to handle 5 transactors or 5 processing elements. NOCs are built typically to handle hundreds of processing elements. So you may be able to verify a little configuration here and there, but the silicon design houses need confidence to happen at the largest configurations. And most importantly, when software comes into the loop, we need to understand the entire interaction from the software down to the hardware. So yeah, there is a lot happening. And as you know, fabric ties everything together. So if things start to go wrong at the NOC level, fabric level, then it can be very difficult because almost everything is impacted. Your whole SOC is impacted. I mean, if you have one glitch in a processor or a GPU, yes, you're going to turn it off. You can lose one feature, but you're not going to crash the whole SoC. My feeling is that if knocks go dramatically wrong, you can actually bring down the whole SoC, and then that's going to be more expensive to patch.
So where does formal fit into all this?
So what you're seeing here is a grid in front of us where all processing elements are connected to each other via routers, which are red dots here. And what we are looking to verify is that the data gets routed correctly according to the routing rules of the NOC. From each source to the destination, the data does not get corrupted, duplicated, lost. There isn't a deadlock, there isn't a live log. QoS, quality of service, as we call it, is correctly implemented. So, apart from all of that, you might want to save power and you might want to put some of the NOC in a certain power island. So, you may have implications of low power as well to consider. Trying to verify this with formal is a gigantic amount of work because we have to look at each router itself and then its interaction on the grid. So let me explain to you why we are doing this with formal in the way that we are. Okay, yes, the bare minimum we want to do is to check the router correctness and its relationship on the grid with other routers. Everybody who is a formal verification practitioner would know that abstraction is the best way to do things. And we, of course, invented lots of abstractions in publications externally. We have been using some of these abstraction models internally. They are efficient, they are reasonably complete in looking at all the interactions. They're quite rigorous, they don't miss bugs. Scalability was handled through a manual step of proof engineering, and reusability, of course, was always kept in mind. But the problem is that when you are leaving it for a human to actually handle the scalability task, the end outcome can be a little bit non-deterministic. And that's what we are trying to root away. Let me actually show you an example of a property that we wrote to verify the correctness of data that goes from one source to a target. And let me show this in the context of the environment where we do not use any of the new technology that we have recently built. What we're saying here is that CoreProof is a technology we have actually built specifically targeting proofs for NOC and other designs. And without CoreProof, we do not actually see a lot of progress. So what you're seeing on the screen is an end-to-end data check that actually tracks the progress of data that is sent from an initiator to the target. And what you're seeing is a very, very finely optimized end-to-end data checking property in formal. We left it running for 22 hours. And what you're seeing is an output of Jasper Gold, Cadence's formal verification property checking tool. And you can see that these numbers that are reported here, there is a bound of 66. So now it gets very interesting, and these numbers actually are very important for us to notice. So the tool is telling us that after 66 clock cycles, it was not able to find a proof. Okay, fair enough. So what do? We could run it for longer, or we can change the tack. So let's run with CoreProof. Let's bring in our technology and see what happens when you do that. So when we actually enabled the abstraction layer and the proof engineering properties that we have coded by hand and optimized it for domains like NOx, what you're seeing on your screen is that 22 hours of no proofs became a proof in 1 minute, 19 seconds. That is the power of abstraction when it's done right. What you're looking at the bottom half of the screen is a slight variation of the problem where we are showing that it doesn't matter whether you're tracking 1 byte of data or 8 bytes of data, the proof times are still quite reasonable, under 5 minutes. The question to ask here is, okay, fine, we can find these proofs, but are they so important, or is bug hunting more important? I often hear the people say that, why waste so much time trying to get these full proofs when you can find bugs?
So are you sure you're actually catching a bug? What's your proof here?
Let's look at a case where we may have a bug, and let's look at whether we can catch it and whether this technology is actually even needed to catch it. So what we're looking at here is the next level of decomposition that has been done on the master check. So this property, which is marked in red, is the end-to-end data check that got proven in 1 minute, 19 seconds that I was discussing earlier. Now there is a bug in the design. And what we have done is to decompose this end-to-end check into more checks, one for each link on the grid. And what we're seeing is fascinating. All of these link checks have proven. And these are the engines that come out of Jasper that tell us that different engines have found a proof. Awesome. What we don't know yet is whether there is a bug beyond the bound of 55 in 40 hours of runtime. This is really the pain point in Formal, us not knowing whether or not there is a bug. We can keep it running. So we kept it running for 48 hours. So after 48 hours, it has still not given me a yes or a no answer. We could keep running it for longer, for weeks on end. This is not going to go further. Why do I know this? Because the Jasper's proof grid infrastructure tells me how much memory has been used. And you can see in the top right-hand corner, the page faults have started. We have consumed almost all of the 1.5 terabyte RAM. 96 CPU cores are running, all trying to verify this particular problem. Different Jasper engines are producing different bounds. We don't have a proof or a disproof after 48 hours. The question to ask is, what is the expected bound for the master check for sign off? And if there is a bug that we have caught. And this leads me into thinking that we need a better way to solve these problems. And that's what we are looking at, Ed, because at this stage, most formal verification teams hand over the stuff for sign off and they say, we're going to use bounded sign off. I don't know what to tell you which bound is necessary or which bound is adequate. I cannot make that judgment call, and therefore I cannot tell you if there is or isn't a bug. So the only way to find out is to try a different tactic, which is to go and write these bug hunting assertions or use the proof engineering infrastructure.
You also don't know how important a bug is for the operation, right? Because this can vary depending upon workload. It can vary depending upon the hardware that's involved. I mean, there are all sorts of variables here that can play into this.
Yeah, indeed. In fact, in this particular case, do we even catch this bug and how deep is this bug? I mean, notice that the bounce we're getting here is 115 clock cycles after reset. So at least there is one engine that has tried 115, whatever that bounce mean for Trident engine in this case. What happens is that if you actually look at the nature of these bugs, so in this case, one of the properties we have in the tool happened to have fired. And let's take a closer look at this property as to why this failed and what kind of bug was sitting, not showing up in the end-to-end proof. So actually, several properties have failed. We've picked up the one that has failed in the least amount of time. Showing here is 4.6 seconds of wall clock time. In this case, the wall clock time and the CPU time is identical. Normally, the times reported in Jasper is CPU time. The bound of 100 means 100 cycles after reset. So what's happening here is that normally in any protocol, the understanding is that if you're reading something out of a FIFO and you're trying to write it to the other one, then the receiver has to have space to be able to take it in. This particular bug has been planted in between FIFO 1 and 2 to say that actually, in this case, it is not important for me to look at whether the subsequent FIFO was full. So we commented out, so the receiver is not seeing that coming in. And what happens as a result is that you see this coming out of link one, and the write to link two cannot take place as the link two buffer is full. And what happens is that this bug source is at the beginning of the transaction. The check itself is tracking the very first source and the very last target. So this, in this case, could be 7 or 8 deep, the 8 routers on the way, which is a pretty big configuration for any NOC. So how are you going to find it if you're not going to actually try and look at it in a different way? So this kind of bug actually is the signature bug in many different examples of our interactions. That's why we brought this up here. We can catch it if you were to track it properly.
So one of the problems that we've been dealing with formal is that there's a reputation that it's slower than some of the other tools that are out there, but also does it scale, and that's sort of tied together. What's changed?
So it is perceived as slow because it's exhaustive. So it's trying to consider all possible interactions. And as I just showed you, in 48 hours, if not done properly, there is, of course, a problem. When we do it properly, it scales quite nicely. So this graph actually shows you how the proof time is scaling up when the number of routers keep on increasing. This particular graph was constructed on the same problem space that we looked at. And we were able to expand the number of routers all the way to 128. And we were able to run the same infrastructure to see whether the proofs A converge when there is no bug, and B, when we have different kinds of bugs, do we catch them? So this made us believe that actually formal verification of knock grids is now possible.
So you're talking about scaling. Does it work on much larger NOCs? Because these things are just becoming enormous. You've got a lot of data that's moving through here.
Absolutely. So we've been looking at an open source knock, which is called FlueNock. It's quite an interesting knock. It is designed by the Pulp platform team and is designed for high bandwidth. And it supports, AXI4 with tops from AXI5. It has multi-burst. It has the concept of VCs. It has a reorder buffer as well. So a fairly complicated protocol implemented in a knock that is actually fully configurable. So FlueNock is a knock code generator, so it can generate lots of different knocks. So we said, okay, we'll look at this and see whether we can actually start to find bugs and get proofs. So I want to give you a very quick overview of what kind of knock this is. So there is an AXI router and an NW router. In an AXI router, there are two independent physical channels, one for request and one for responses. So this seems to be the flavor in most knocks. They have 32-bit address and 64-bit data. And there are three independent physical channels, one for AR, one for B, and both have 32-bit address and 64-bit data. And the third one for AWW and R. If you look at the payload that this carries, it can be as wide as 512 bits. And each router has five different directions, northeast, southwest, and itself, the local one. If you look at now verifying a knock grid with a 2x2 mesh, there are three routers in the path, and in a 4x4, there are seven routers in the path. So what we're looking at is verifying all of the source target combinations simultaneously, looking at all of the paths. So for example, if you look at the longest path on a 4x4 and it's an X first routing, you're talking about verifying this path and this and this and this. And these are the longest paths. So not only are we verifying all of these, but also the point to point between each router, the shorter ones as well. And I think what we're seeing here is that when things are connected to each other along the longest path or the shortest path, there is a lot of back pressure piling up from previous transactions, and they can all easily create problems in us not being able to either prove things or bugs, head of line blocking, arbitration blocking, starvation, all kinds of bugs show up. So this is a fairly large configuration, if you ask anyone in the NOC design community. So this is the kind of configurations we've been looking at.
So what was the result of all this? What did you actually find?
When we throw this knock inside Jasper, 94 out of 96 key properties remain inconclusive after 5 days of timeout. But when we actually put the same knock inside our app knock proof and we set it up with no test bench code to be written, just the configuration side, hit core proof, what you then see is the proofs start to come out exhaustively. And in fact, they come out quite quickly in 37 minutes, 40 seconds on the router level. What is interesting is that if you go to the grid level, you start to see the proofs come out for 2x2 mesh, 4x4. In fact, the proof for the 4x4 mesh actually takes less time than a direct flight between London and JFK. So you can actually get an exhaustive proof on such a large configuration with this kind of method. We can look at without VCs, we can look at with VCs. Most of the results are exhaustive. In fact, all of them are exhaustive. So we can show you that we have been profiling and testing these configurations, different gate sizes and different flop counts. So some of this is reasonably big. A 4 by 4 on a FIFO depth of 8 is about 18.8 million gates with about 6,289 instances. So yeah, these are the kind of results you can get.
So formal has suddenly become much more important for moving data around than it ever has been looked at in the past, right? I mean, this is all about moving data and making sure that it gets to where it's supposed to go and back again in the least amount of time and also at the proper time and making sure that all these pieces work together.
Absolutely correct. Yeah. So that is a very nice abstract way of capturing where formal's greatest value is coming is in data transport and checking the data moves correctly. In the context of Knox, of course, things are more interesting with coherent Knox and the interplay along with functional safety and security. I think my point is that simulation alone is not adequate, and we need to adopt more and more formal, and we need to think about going beyond bounded proofs for us to be able to actually find those nasty bugs that could lead to silent data corruption or a deadlock that can actually cause you a respin.
Ashish Darbari, thanks for a great explanation.
Thank you, Ed. Thank you very much.